All right, perfect. So yeah, hello everyone. I'm Malte Buschmann. You will see GRAPPA at the University of Amsterdam on all of my slides as my affiliation. I just moved here 2 weeks ago, so actually all of the work I will be talking about was done while I was at Princeton. Just wanting to point that out real quick. Now, given that I'm talking about axion-strings, a lot of the introductory slides that I have are looking actually very similar to what Giovanni just talked about, so I will be able to go over them relatively quickly. Still want to say a couple words about them just to make sure that everyone is on the same page, even though it should be relatively familiar for a lot of you. So in the early universe, you just have your complex scalar field, your Peccei-Quinn field. The axion is the angular component of that scalar field. The other component is the other degree of your freedom, is just your radial mode, the radial component of your field. In this complex scalar field, the potential at the very early on, it just looks like your normal thermal spectrum. It's then spontaneously broken at the PQ breaking scale Fa. Gets your normal Mexican head-like potential. And then at temperatures much smaller, around a GeV or 0.4 GeV or whatever you want to say, that's actually at the GeV scale, it then gets explicitly broken by the QCD phase transition and looks something similar to this, which is in this case just your domain wall number 1. So you start forming domain walls over there. At that point, your axion becomes massive. Axion strings are then nothing else but topological defects, basically field configuration, where your field, your complex scalar field, is stuck at the central hilltop and is unable to roll down easily. These topological defects are called axion strings, and they're called strings because in 3 dimensions they actually form closed loops. Since they are closed loops, they have a typical size, which is given by Hubble, given that that's your typical rotation length at the time that they form. They also have a width, which is given by the radial mass, since that gives the size of the central bump on which those axion strings form. Now, generally, they exist during the PQ and the QCD phase transition, though they do take some time to decay, which will come important a little bit later. Now, given that the size and they have a size and the width, which is given by these two quantities, what Giovanni already pointed out is that this is actually computationally, if you want to do it numerically, quite a bit of an issue, because the scale separation, while it is order 1 very early on, just due to being in a co-moving universe, the scale separation becomes very, very large. And at the time you would have reached the QCD phase transition, the scale separation between the width and the size is about 70 e-folds. So the strings are incredibly width compared to their size. Now, what Giovanni also already introduced is that basically these axion strings are usually just relevant in the post-inflationary scenario. The reason is that inflation happens after the strings are formed. Inflation will basically just zoom in some spot in between those strings, and all of our observable universe basically just starts with some homogeneous value that your misalignment angle theta 0. In the post-inflationary scenario, however, well, inflation has already happened, so you don't zoom in anymore, so you have your incredibly homogeneous initial state, which has the advantage that you're not sensitive to this one randomly chosen value, but you're only sensitive to the statistical mean of all possible values between 0 and 2 pi. And that is something that we can analytically compute. So effectively, you have one free parameter less in the post-inflation scenario. And the only real parameter in your theory is your breaking scale, Fa. Now, given that you have one free parameter, the really nice implication is that we can actually compute what that is in theory, given that we have one measured quantity, the dark Rayleigh density. In order to match these two on top, and I think Kenichi's tomorrow talking about that a little bit more in detail, how that is done in practice, is one of the main motivation why I started looking into axion strings a couple of years ago, because you can actually use it to predict what the QCD axion mass is in that scenario, in the post-inflationary scenario, if you have a domain one number of 1. The only thing I want to say real quick is that we are still very much actively working on that. and we are running larger simulations of the PQ breaking scale. We're also running more systematic tests, including the QCD phase transition. And what you're seeing here is basically in both sides just the energy density in axions projected down from a three-dimensional simulation. And you can see these axion strings stand out here and do their thing. On the right-hand side, you then also see these domain walls form, and if you look closer, you can even make out oscillons, about which we've heard yesterday more. Now, these simulations are incredibly difficult because of the scale separation. So even our biggest simulation that we can feasibly run using adaptive retrieval and other techniques, you can really see how large the scale separation is. You have to zoom in multiple times in order to even resolve the string. And that's just why these simulations take millions of CPU hours to run. But again, I think Kenichi is talking about this a little bit more in detail about why these simulations are hard and most importantly, actually incredibly hard to interpret as well. The thing I really want to talk about today are signatures of axion strings. So if you think about signatures, before I want to introduce what those could be, you need to think about in what situations you even expect any signatures. And if you go to the normal QCD axion with domain number one, the one that I've just talked about mostly, you're actually kind of out of luck. And the reason is that your string network starts to decay around the QCD phase transition, as shown in one of our older simulations over here. That decay is not entirely instant. As we've heard earlier, the axion starts to become massive QCD phase transitions start oscillating around when the axion mass matches Hubble. But typically around that time when it starts to oscillate, the network is pretty much gone. Unfortunately, for a QCD axion with domain number one, the mass of the axion is around a couple micro eV, which means that by the time the network you reach anything interesting like BBN or anything like that, the network is actually long gone. So even if the network interacts with the standard model soup in any non-trivial way, any of these signatures will have just thermalized away. So essentially, your string network just doesn't live long enough in order to have any other like direct signatures that you might be able to observe. It's still important to study it to get the dark matter mass in terms of the QCD axion, but we need to think a little bit differently if we want to look for other signatures. Unfortunately, we know that the network, even if it starts to decay around the QCD phase transition, it will survive until the axion starts to oscillate around its VEF. So if you consider much lighter axions, for example, you consider a mass that is lighter than 10 to the minus 23, you expect it to actually survive until BBN. Similarly, if it's lighter than 10 to the minus 29, you even expect it to survive to the CMB. And if it's lighter than 10 to the minus 33 EV, they can even survive until today. So whenever I will refer to axion strings today in this talk, I actually mean axion-like particle strings, so ALP strings. Now, of course, ALPs are not the only way to have your string network survive until today. Of course, if you have a domain one number larger than one, your string network can also be much, much more long-lived, as we said earlier today. So there are the other ways, but then you also have domain walls. So just for simplicity, I will just refer to ALPs for today. And particularly, I will refer to a relatively light ALPs that are lighter than 10 to the minus 23, just so that we have any observable signatures. So what are those signatures? There are generally three different types. One is, of course, gravitational waves. We have already heard a little bit about that too. They just contribute to the stochastic gravitational wave background and work from Marco and Ed and Hiro and so on. That's a signature that could potentially be observed. Similar CMB birefringe. In the last couple of talks, we've already heard that a little bit as well. Axions can rotate the polarization of CMB photons. So if you have an axion strings, it's a very striking signature that you expect. And it just, is a potentially observable signature as well. But the one that I really want to talk about is the third mechanism, and that's just production of standard model particles. And the basic idea is that axion-strings produce standard model particles, and how they do that I will in a second. And then once you produce the standard model particles, they can inject energy during BBN, CMB, or also just produce gamma rays at the present day. And those are signatures you can potentially detect, because the story is very similar to basically just annihilating dark matter, which also injects energy during these times. But in this case, the energy becomes from standard model particles produced by axion strings. So we all know axion strings emit particles. They are the main production mode of axions, which is why we are running these large-scale simulations of axion strings, because in case of the QCD axion, we're trying to understand exactly how much are emitted as a function of time, so we can compute the number density and then match that onto the dark matter relic density. But axions are not the only particle that is being emitted by axion strings, because after all, you're simulating a complex scalar field, and the axion is just one degree of freedom of it. The other one is the radial mode. And of course, you're also producing radial mode particles. That overall is kinematically suppressed just because the radial mode has a mass, it's relatively heavy. So at small k, it's heavily suppressed. But you know, at large k and so on, you can still produce them, even though they're heavy. They're subleading, but we're so interested in that because the radial mode actually decays, because it is so heavy, into standard model particles. The exact branching ratios are heavily model dependent, depending on how exactly you implement your ALP, but it can decay into, you know, your typical bosons, WWZs, gammas, photons, and also the Higgs. It is quite model dependent in total, and you know, one of the main decay channels, of course, axions. But if you look into how much decays in the standard model particle, depending on your model, it can be almost order 1, your branching ratio. So what we then want to know is, of course, how many radial mode particles, what is the emission rate of radial mode particles of axion strings? And that, if my slides don't want to advance anymore. There we go. So what we want to know, of course, is the emission rate. Yeah, the emission rate that you actually saw on the previous slide over here, those are basically a function of Hubble, of course. They depend on chi here as the string length per Hubble volume. Of course, the more strings you have, the more you emit. And the other factors here are coming from the string tension. This formula over here is a conjecture. In particular, we don't know per se what this numerical factor C over here is, the prefactor, the normalization of the emission rate. We can estimate it, of course, through analytic or semianalytic means. So what we did is, for example, we assumed that the emitted modes of axion and radial mode is equal below for k smaller than the mass, and above it, it's not present essentially. And we just studied, you know, your normal straight string, and we used that to estimate what C would be, and we found a number of 0.1 once we integrated over the different modes. But of course, the proper way to do is through numerical simulations, because well, the string network is not just a straight line, it's actually much more complicated. You have your reconnections, you have your kinks, and so on in your field. So essentially, that's what we did, is we ran dedicated simulations in order to measure the radial mode emission. Now, normally we run these kind of simulations in an adaptive mesh, because typically we need, of course, a high resolution around the axion strings in order to capture the UV physics properly. But away from strings, we usually don't care that much about resolution. We don't need such high resolution. That's something we see in this image over here. And over here, you can see the different refinement levels. Unfortunately, in this type of simulation, we can't actually do that. We have to run it on a static mesh instead of an adaptive mesh. Because it is suppressed at low K, we do actually care about the really high K parts of the radial mode emission spectra. If we would just be interested in the axion emission, we wouldn't care about that. It would be perfectly fine to just average out this very small emission of the radial modes. But given that we are actually trying to measure that one now, we needed to go to a static lattice in this particular case. Long story short, we ran a couple of these simulations. We can, from those simulations, directly extract the energy density for the axion and then also for the radial mode. The slope essentially tells you your emission rate. Of course, because we are running on a static mesh, we were somewhat limited in how far we can evolve and how much statistic we accumulate, so the data isn't particularly great, but that's just reflected in that our numerical factor that we then extract from simulation has a relatively large error bar. But in large, it is relatively consistent with also what we got from our analytic estimates. It's somewhat larger, but that's not actually unexpected, given that in our simulations we have all these kings that we can see in this image over here. So it's not, yeah, it basically makes some sense that it is a little bit larger, but it's somewhat consistent. So yeah, this is the emission rate from just radial modes that can then decay into standard model particles. But that's not the only way you can produce standard model particles with axion strings. The other method is through a coupling to the Higgs. Because generically you expect to have some kind of term in your potential that looks something like this. You just couple your Peccei-Quinn field to your Higgs field. Now, if you do that, what we did is essentially we simulated our normal PQ field, but simultaneously also then included the Higgs field and have them both coupled through this kind of term. What you see here in these two images is just a slice through a 3D simulation. You see axion strings stand out in the axion field values as basically just being a pole, given that your axion strings are by definition in the center of your potential, so they stand out as a pole. In the radial at most, you see them as bright spots, given that most of your field will be just oscillating around the VEF, exactly axion strings. And then if you look at the Higgs field, you actually see that it mimics quite a bit what you see in the axion string. That is, your Higgs field doesn't actually oscillate around its VEF. It actually has field excursions, quite massive field excursion at the locations of the strings. And those are really just coming from the reaction of the axion string onto the Higgs. So basically, the axion strings are injecting energy into the Higgs field. So if you start plotting the energy density in the Higgs, it actually starts looking very similar to what you see in the axion field. It basically mimics very much what you see there. So essentially, axion strings don't only produce axions, they also produce indirectly through the coupling Higgs particles, which then, of course, decay further into other standard model particles, which then inject energy into the CMB, PPN, or whatever your axion mass is in that particular case. Of course, we are running dedicated simulations of those as well. Those are a little bit model dependent, depending on what parameters you have in your potential. What you see here is the emission rate. So the gray line is the Higgs emission you expect from producing radial mode particles that then decay into Higgses. Versus the data points, which are coming from these kind of simulations where you're directly producing the Higgses through the coupling and the potential. And depending on what your potential really looks like, either of those two can dominate. So you really need to take into account both of those production mechanisms. So with that, we can jump straight into observational constraints. First of all, I want to go just summarize a little bit of existing constraints independent from axion strings. First of all, we have constraints on FA because it needs to be smaller than the reheat temperature. Otherwise, you don't have axion strings because you're not in the post-inflation scenario. Then you also just get contributions to N effective during BBN and CMB, which are coupled 10 to the minus 14 GeV. Same, you have gravitational effects that can imprint itself on CMB and can cause CMB anisotropies, which again has a constraint on the breaking scale. But of course, these constraints are only relevant for masses smaller than these, because otherwise the string network actually doesn't live long enough in order to be even around your BBN and CMB. So coming to the constraints that we are trying to derive here is we already know the energy or the different emissions rates, which allows us to basically compute the energy that is injected coming from strings during the different epochs. And that is really just a function of the string length at the time of injection, Hubble, as well as your different branching ratios, and then your various different numerical prefactors of how much you actually emit. Once you have that, it's actually pretty trivial to derive these constraints because it looks exactly like decaying dark matter, annihilating dark matter, which also inject energy. It's the source of that energy is very different, but from a just purely analysis point of view, it's pretty much the same.
5 minutes?
Yeah, I'm about to be done. So the constraint we find during BBN is order of 10 to the minus 14 GeV as well. Of course, it depends on the exact emission rate that you find, in which case this would be order 1, your model-depending branching ratio, as well as the string length at the time of BBN, which is somewhat of a function of what your axion mass is. If it's much lighter than this number would be quite a bit larger. Now, this constraint overall is is quite a bit stronger for N effective if the branching ratio is larger than 0.01. You can do the similar exercise for the CMB. In this case, you find that it is smaller than 10 to the minus 11, which is also quite competitive. Again, it depends on the different factors, your branching ratios and your string length at the time of the CMB injection. The analysis here is a little bit more complicated because, of course, we need to run class and dark history and so on, these different tools in order to compute exactly what the spectrum is like, and then run the normal log likelihoods. But this is effectively the result we get from doing that analysis. And then if your axion mass is lighter than 10 to the minus 20, 10 to the minus 33, you can actually observe direct gamma rays coming from these axion strings if they exist. In this case, what we did is we just reinterpreted searches for extragalactic dark matter decay, given that the signature is pretty much the same. Also, in this case, we get somewhat competitive bounds depending on what your exact branching ratio and your string like this. And that already brings me to the summary. So we have axion strings. We assume that the axion in this case is an ALP, and that it is relatively lighter than 10 to the minus 23 at least. If they are that light, they can produce standard model particles, which then inject these the energy into the BBN or the CMB or produce gamma rays. We can use that to place competitive bounds depending on your exact model parameters. And thank you.
Okay. Thank you very much for the nice talk. And so we have some question. Wen John, please.
Yes. So actually, I have 2 questions. The first one is that it's because there's coupling between the axion and the FF tilde. So there should be, I think the axion string can also emit photon pair. So why this has not been considered in your work?
I mean, this is your gamma rays, right?
Okay. So yeah, because so in this talk you mentioned the emission of radium modes and also axion modes, but there's directly emission of the photon. So you think this is already taking into account in the gamma ray constraint, right?
Yeah. Yes, if I understand your question correctly, yes, the answer is taken into account here.
Yeah, and also my second question is that actually the particle production is kind of quantum effect. So in your simulation of, for example, the string, how do you take this effect into account? Do you actually just put a friction term, some term like it, into your equation motion for the axion field, or how do you take it into account in this?
I wasn't entirely sure what you said. What kind of effect?
particle production. So if you study the axion field cluster equation motion, then you can never see the particle production, right? I mean, your string can emit particles. Then I think this is kind of I can imagine that there's kind of friction term in the equation motion, in the classical equation motion. I want to check it's correct or not.
Yeah, so in our simulation, we just solve the classical field equations in this case, and we compute the emission rate just as the slope of the energy density in that case. So it's all done completely in the field in the classical field view.
Okay, yeah, thanks.
Okay, so now we have a question from Daddy, please.
Hi, Malte. Just very quick question. Which way round should I be reading the limits here? So I think it's a limit from a coupling. So you're excluding small values of f, right? So this is so for example, the top one, you're excluding f less than 10 to the 14 GeV for this range of masses. Is that the right way around to read the limits?
So okay.
Is small f allowed or big F allowed?
It's an upper limit. Right? Because if you make your branching ratio larger, this value gets smaller. And if you make your branching ratio larger, you expect your limit to become stronger. So it's an upper limit. So FA smaller than these are allowed.
FA smaller is allowed. So that means you allow bigger G?
Hold on. Small.
FA smaller is excluded, I think. But
I should.
But bigger F means more density, but bigger F means weaker couplings. So that's why I'm just confused about exactly what the limit is.
Right. No, I believe those are upper limits, right?
Okay. So the limit is really is coming from how much energy density is in the network, which is set by F, rather than by the strength of rather than really by the strength of the coupling.
Yes, exactly.
Got it. Thanks.
So last question from Sebastian.
Yeah, hi Malte. One question. Did you also consider spectral distortions, so from Firas and Kobe? Or does that not play a role?
We have not.
Because I mean, generically speaking, whenever you have energy injection, that you might get, depending of course on the value of FA and so on. But yeah, I was just wondering, maybe.
Yeah, I don't have a good answer for that. It might be that we had considered it and then discarded it. We went through a couple of these where it just wasn't competitive. I would need to double check whether that was part of it. I don't honestly remember.
Okay, cool.